All right, welcome to lecture 10.2, covering non-right triangles, the law of cosines. Now in 10.1, we covered non-right triangles as well, but we covered it using the law of sines, which is useful when we're given an angle, an included side and another angle, so angle, side, angle, or if we have an angle, angle, side triangle. And then we even looked at the case of the angle, side, side, which was the ambiguous case. So the law of cosines is going to cover triangles that are of the form side angle side, so we have an included angle, but we don't have one full set of an angle with an opposing side, or a side, side, side triangle. That's what we're going to use the law of cosines for. So let's go ahead and look and see how we come about deriving the law of cosines. Okay, so with the law of cosines, as stated on the last page, this is used for non-right triangles. And what we do to derive it is we put a non-right triangle in our XY plane, and we create the associated right triangle by dropping a height down from the vertex C, and using our right triangle trigonometry knowledge to come up with an expression for side A there. So let's go ahead and move into looking at the details of the law of cosines here. Okay, so the first thing I'll point out to you, and this is something that we learned a couple tests ago, is that the cosine of theta is equal to the adjacent over the hypotenuse. And in this particular case of the blue triangle, the right triangle that is formed by dropping that height down, the adjacent side to angle theta is x. That's the adjacent side. And I'm going to divide that by my hypotenuse, which is the same hypotenuse. Well, it's not called a hypotenuse in the blue triangle because that's not a right triangle. But it forms that long side of the non-right triangle, but it also forms the hypotenuse of the right triangle that we formed, and that is side B. So this is the hypotenuse of that right triangle we formed. Then we also have the sine of theta. And sine is opposite, which in this case is our y value, or that distance y. So our opposite over our hypotenuse, which is b. Okay, and then if we solve for x and y in both of these equations, all we have to do that is multiply both sides by that b value, because that gets it out of the denominator there. Same thing over here. And I end up getting expressions for the x and y coordinates of point C here. And here's what I end up with. I end up with the x coordinate being equal to b times the cosine of theta, and the y coordinate being equal to b times the sine of theta. So you can see that's why they have listed B cosine theta, B sine theta. Now remember, that point C does not sit on the unit circle. If it sat on the unit circle, we would know that the coordinates were cosine theta, sine theta. But because it's an arbitrary point, we can use this right triangle Pythagorean relationship to find those expressions for the x and the y coordinate. Okay, so if we want to find an expression for this side A here, notice side A is actually the hypotenuse of this very small right triangle that we formed. And if this entire side here is x, and this length right here of the blue triangle is C, then we know the bottom leg of the small right triangle has got to be x minus C. That's the total x minus the value C there. And then we have y as our value for the other leg of the triangle. So here we can use our Pythagorean theorem that says a squared, that's my hypotenuse, is going to be equal to b squared plus c squared. So, well, not b squared plus c squared. We usually have our Pythagorean theorem written as a squared plus b squared equals c squared, but a squared is our hypotenuse, and then it's the squares of the legs that get added to equal the square of the hypotenuse. So we can further modify this because we have trigonometric expressions for x and y. So I can come in here and say, well, x is actually b cosine theta, and I'm subtracting that c value plus our other trigonometric expression, b sine theta squared. Okay, and then if I just begin to use my algebra skills to find the expression for a squared, I'm actually going to multiply b cosine theta minus c times itself. That's just squaring it. And I don't like to square in my head. I would much rather write it out like that and do the distribution. And then this last term ends up being b squared sine squared theta. Okay, now I'm going to go ahead and do this distribution here. And I get a squared is equal to b squared cosine squared theta minus bc cosine theta minus bc cosine theta plus c squared plus b squared sine squared theta. Okay, and I see that I have a common factor of b squared in both of those terms, and I've got like terms right here. So I'm going to rearrange and combine those like terms. So I get a squared is equal to b squared cosine squared theta. I'm going to go ahead and bring that last term next to this one, since it's got that common factor of b squared, sine squared theta. And then I'm going to combine my like terms in the center there. That's a negative 2 bc cosine theta plus c squared. Okay, the reason I rearranged those was so I can factor out that b squared, and then I'm left with cosine squared theta plus sine squared theta, and that should be ringing bells and whistles in your head right now. Way back from when we first started studying trigonometric functions and identity properties, this is our Pythagorean identity right there in the parentheses. This whole thing is equal to 1. Cosine squared theta plus sine squared theta equals 1. So that just becomes 1. And what we end up with is a squared is equal to, well, b squared times 1 is just b squared. And then I'm going to bring up that c squared just to make it look neater, minus 2 bc cosine theta. That is one of the forms of the law of cosines. The other two forms just solve the equation for b squared and c squared by just algebraic manipulation there. So that's where we get the law of cosines from. And you can see we have it in 3 different forms here, solved for each of the sides. Well, each of the sides squared. And then we're also given the same laws of cosine solved for their respective cosine of the angle. So depending on what you're needing to find, a side length or an angle measurement, you can use either form. So that's what we're going to do, is just use the law of cosines. All right, so we are given information about a triangle, some non-right triangle. We're told that angle alpha is 30 degrees. So this would be angle beta. This is going to be angle gamma at the top there. Across from angle beta is side B, which is 12. And across from angle gamma is side C, which is 24. So what we're dealing with here is a side angle side triangle. We have a side, the included angle, and another side. And since I'm trying to solve this triangle, my first task is to somehow get the measurement of one of my angles and its opposite side so that I can set up the law of sines and use that, use the law of sines to complete solving the entire triangle. So that's what I'm going to do. And since I'm needing side A, that's the first side I'm looking for, I'm going to use this version of the law of cosines. Okay, so that particular version tells me that a squared is equal to b squared plus c squared minus 2bc cosine alpha. All right, so a squared is equal to 12 squared plus 24 squared minus 2 times 12 times 24 times the cosine of 30 degrees. So a squared is equal to 144 plus 576 minus 576 cosine of 30 degrees. A squared is equal to 720 minus 576 cosine 30 degrees. Now I'm ready to take the square root of both sides. And I don't have to take into consideration the negative because we're talking about a distance here. And there's no such thing as negative distance. So we'll only consider the positive. And when I put the square root of 720 minus 576 cosine 30 degrees into my calculator, I get that A is approximately 14.9. So here's what I found out right there. Now all I have left to figure out is angle beta and angle gamma. And I'm going to use the law of sines to do that now that I have my angle with its opposing side. I can set up that proportion with the law of sines. So I have the sine of 30 degrees over 14.9 has to be equivalent to the sine of beta divided by 12. Okay, so I'm going to cross multiply here. 14.9 sine beta equals 12 sine 30. I come back and divide both sides by 14.9. And I get the sine of beta is equal to 12 times the sine of 30 degrees divided by 14.9. Well, I don't want to know what the sine of beta is. I want to know what beta is. So the arc sine of 12 times the sine of 30 degrees divided by 14.9 is what's going to give me a measurement for beta. And when I put that into my calculator, I find out that beta is approximately 23.8 degrees. So now I know beta, 23.8, and I can use my knowledge of the sum of the interior angles of a triangle to figure out what gamma is without having to use either of these laws. So 180 minus 30 minus 23.8 leaves me with 126.2, and that is the measurement of gamma, 126.2. All right, ladies, do y'all have any questions about how I used the law of cosines or law of sines to solve this triangle? If not, just give me a green check to let me know that you're good to move forward to the next triangle. Okay, Crystal, I see you're typing something. And I see you gave a green check also, so I'm going to go ahead and move forward while you're typing. Okay, so we have another situation here. This time we're given 3 side measurements of a triangle. So this is going to be a side, side, side triangle. So we have angle alpha here, angle beta, angle gamma. This makes that side A, this side B, and this side C. Okay, so we have measurements for A, B, and C. We're given those, 5, 7, and 10. All right, so we just start with any of the sides. Actually, I take that back. We start with any of the angles. All we need to do is find the measurement of 2 of the angles, and then we can use the fact that the interior angles sum to 180 to find the third one. So I'm actually going to use this version of the law of cosines, and I'm going to solve for alpha first. So the cosine of alpha is equal to b squared plus c squared minus a squared divided by 2bc. Okay, so that is equal to 7 squared. Oh, okay. It must have just picked up that you had clicked in or something, and now it's stuck there, Crystal. Sorry. Okay, plus 10 squared minus 5 squared divided by 2 times 7 times 10. Okay, so this is 49 plus 100 minus 25 divided by 140, and that gives us 124 over 140. That's the cosine of alpha. But once again, I don't want to know what the cosine of alpha is. I want to know what alpha is. So I take cosine inverse of 124 over 140, and that's going to give me alpha. And when I put that into my calculator, I figure out that alpha is approximately 27.7 degrees. So here's what I know. I know that alpha is 27.7 degrees. And now I'm going to do the same process for beta. So the cosine of beta is equal to a squared plus c squared minus b squared divided by 2ac. And I'm just going to plug in my values. 5 squared plus 10 squared minus 7 squared divided by 2 times 5 times 10. So that's 25 plus 100 minus 49 divided by 100, which is 76 divided by 100. Remember, that's the cosine of beta. So the cosine inverse of 76 over 100 is beta. And beta is approximately, when I put that into my calculator, 40.5 degrees. So now we know beta. And all we have to do to find gamma is subtract the other two angle measures from 180. So 180 minus 27.7 minus 40.5 is equal to 111.8. So our triangle is now solved. 111.8. All right, green check or red X? Ladies, are y'all okay on this one? Great. Okay, and now we have an application problem. So suppose a boat leaves port and travels 10 miles, turns 20 degrees, and travels another 8 miles. How far from the port is the boat? Okay, so there's a slight, very, very slight bit of cleverness involved with this. And if you notice, when the boat turned 20 degrees, that 20 degrees is not an angle that is on the interior of the triangle. So what I have to do is subtract that 20 degrees from 180 to figure out that that angle right there is actually equal to 160. It's on the inside, and we'll call that angle alpha, which means that this side of the triangle that we're trying to find is side A, because that's how far the boat is from the port. So what we're dealing with here is a side angle, side triangle. We've got 10, 160 degrees, and 8. So we know a side, an angle, and a side. So this is a simple one, actually. A squared equals b squared plus c squared minus 2bc cosine alpha. So a squared is equal to 10 squared plus 8 squared minus 2 times 10 times 8 times the cosine of 160. A squared is equal to 100 plus 64 minus 160 cosine of 160. A squared equal to 164 minus 160 cosine 160. Take the square root of both sides. Once again, we don't have to consider the negative, just the positive since we're talking about a distance. And we get that A is approximately 17.7. So the boat is approximately 17.7 miles from port. That's it. Not so bad. Okay, moving forward to the area of these triangles. And we are given a formula, and this is a pretty important formula. This is going to come up again in your calculus class. And it's Heron's formula. And Heron's formula finds the area of oblique triangles when you know the lengths of all the sides of the triangle, but you don't know any of the interior angles. So we have Heron's formula as area equals this value S. And if you look right here, S is equivalent to adding up all the sides, so that's the perimeter of the triangle, and dividing it by 2. So these values S that show up in Heron's formula, you actually have to calculate that value. So it's the square root of S times S minus A times S minus B times S minus C. So let's put this formula into action with these given lengths of the sides of a triangle. So the first thing we want to do is find that value S. And in this case, S is equal to 29.7 plus 42.3 plus 38.4 divided by 2. And when I put that into my calculator, S is equal to 55.2. So now I'm ready to plug into Heron's formula here. Area equal to the square root of S, which is 55.2, times 55.2 minus A, which is 29.7, times 55.2 minus 42.3 times 55.2 minus 38.4. Okay, and that equals the square root of 55.2 times 25.5 times 12.9 times 16.8. And when I put that into my calculator, I get that the area is approximately 552 feet squared. Any questions about using the two parts to Heron's formula, ladies? We've got 2 more area problems to do, and they use the same formulas. So as long as you understand this, you're going to be okay on these last 2 problems. Allie, you good to go on that? Okay. Okay, so we just have a application problem here, but it's an area problem with a non-right triangle. So We're just going to use Heron's formula. A Chicago city developer wants to construct a building consisting of Artist's Loft on a triangular lot bordered by Rush Street, Wabash Avenue, and Pearson Street. The frontage along Rush Street is approximately 62.4 meters. Along Wabash Avenue, it is approximately 43.5 meters. And along Pearson Street, it's approximately 34.1 meters. How many square meters are available to the developer? So, first thing we're going to do is find that value S. And S is equal to 62.4 plus 34.1 plus 43.5, all divided by 2. And when I put that into my calculator, I get that that is equal to 70. So the area that the developer has to work with is equal to the square root of 70 times 70 minus 62.4 times 70 minus 34.1 times 70 minus 43.5, which is equal to the square root of 70 times 7.6 times 35.9 times 26.5. And when I put that into my calculator, I get that the area that the developer has to work with is approximately 711.4 meters squared. That's it. And we've got one more, just a general triangle to work with, just one more set of practice here. So let's see, we've got 4.38, 3.79, and 5.22. And we're just asked to find the area of that triangle. So S is equal to 4.38 plus 3.79 plus 5.22, all divided by 2. And that area, that value comes out to be 6.695. So the area is equal to the square root of 6.695 times 6.695 minus 4.38 times 6.695 minus 3.79 times 6.695 minus 5.22. And when I put that into my calculator, I get that this area is approximately 8.15 feet squared. All right, ladies, that's all I have for you this morning. We are done super duper early, so I didn't jinx us. Yay.